moments in their you know, in their careers, and it's partly the reason why they're here.
Yeah.
I met Carl Pribram once, Peter, and I asked him what did he think of the state of understanding the brain, and he said,
I think that,
and he said, excuse me, he said,
Mike.
I think I say that's what that's basically what that was basically Pribram's third hypothesis.
Can you let Mike finish?
But of course it went it went largely unfinished.
Chairman. Sorry, Mike. What was your question?
No, it wasn't a question. It was a comment that I had the pleasure of meeting Pribram just before he died, and I asked him what was the state of the understanding of how the brain works, and he commented, "We don't even know the right questions."
Wise man.
That's a bit surprising from my experience.
Am I audible?
You're audible, yes.
Yes.
But I'm about to make you inaudible.
That's all right.
I'm going to make everybody inaudible. And Roger, are you ready? Are you ready to go? Do you want to share your screen, and then I'll make everybody inaudible, and you can make yourself audible, and we can hit the road. Week 4.
Wow.
With ambiguous ether.
Hello. Hi.
Hello.
Can you hear me?
Yeah.
Yeah. So share screen. Share. Can you see that?
We can. There we go.
Brilliant.
Good. Okay, I'm going to turn off my microphone and my video.
Yeah.
The floor is yours.
Okay, thank you. Okay, thank you for letting me do this talk. The title is called The Ambiguous Ether, and I'm picking up from last year's talk. I found that Einstein's 1905 paper, what is happening here? Einstein's paper of 1905 on special relativity was mistranslated from German into English. And what I found, that I'm not unique in saying this, I found this book by Arthur Miller, who wrote about it in 1981. And I think what happens is there's a mass of literature on relativity, and issues like this get overlooked, and it does not get into wider attention. And so the issues become such things as, why didn't Einstein become more aware that his theory had been mistranslated into English? And I think the reason is possibly that his wife was a major contributor to the theory. She would have been more concerned about the mistranslation, as it might not have been in agreement with her understanding of relativity. Whereas for Einstein, for his understanding of relativity, the mistranslation did not seem to make much difference. So my pages are moving on, and I don't know why. So this is a talk by Professor Gannon, and she's talked about Einstein's wife. And if I can, I want to show a video clip of it here. So.
Let's talk today about the tragic destiny of Wilhelmina Ripsenstein. As everybody knows, behind every great man, there's always a great woman. So I'm going to tell you about the role of Wilhelmina Ripf, and mostly the plan is to examine how she worked with Albert Einstein for nearly 20 years. And what so her temperament, she was very brilliant, but a reserved person. She was not talkative, but she was persistent and determined. She would go to the end of things. She was someone who would really dig and get to the bottom of things. And she kept going towards her goal. She was someone who knew where she was going. On the contrary, Albert, as many of you have heard, was someone very rebel and a bohemian, and he was someone who was extremely inquisitive. That is very well known, but he was not very disciplined. He could easily change his mind. He hated the discipline of German schools, and that's the reason that he too ended up in his high school in Switzerland. And both of them entered the Polytechnic Institute in Zurich in 1896. This is what is known today as ETH. And they were both admitted to the physics mathematics section. And there were 5 students in the class. Mileva was the oldest at 21 years old. Albert was the youngest. And there was also Marcel Grossman, many of you might know the name, Louis Colvos, and Jacob Erwin. For 1 year, Mileva left and went to Heidelberg to do 1 semester there. And because they were too close, and she wanted to have a bit of distance from Albert. But then she came back. They wanted to be together. So from the beginning, they had this shared passion for physics, music, and each other. Those two were absolutely infatuated with each other. They were absolutely in love. They spent countless hours studying together. The beginning of their collaboration, they started working together from the moment that they met, and they exchanged a lot of letters every time they were on school holidays during the summer when they were apart and all that. So there were lots of moments, Easter holidays, Christmas holidays, and summer holidays where they were separated, and then they exchanged lots of letters. 43 letters from Albert to Mileva were preserved and reached us. And there are only 10 letters from Mileva to Albert that have that remain today. So these letters were published in 1987, I believe, but that's the latest edition, by Venn and Schulman in 1987, and they were published. And so through this correspondence, we can really learn how they were working, how they interacted together. Radmila Miletievich is someone who, she was a history professor at City College in New York, and she published this extensive biography of Mileva, Life with Albert Einstein, and it just got published in 2015. It's extremely complete story. So if you want all the details, you'll get them there. So Radmila Miletievich knows that our news, our viewpoint, our theory, our articles, our work on relative motion. So in those letters written by Albert Einstein, you see that he always says our work. So they had pretty much similar academic records for their 3 years of schoolwork there, with one small exception, that Einstein was known for not being good in applied physics. He was, at one point, apparently, plugged an apparatus one day, they blew to his face, and he got nervous after that. But he was not really skilled with experimental work, was really theories. At one point, he was hesitating. Someone offered him a job, and he had the choice to be an experimentalist or a theorist, and he was asking me, what do you think I should do? He said, come on, whatever. So but that's a small detail that we'll come back to that later. But then at the end of their 3 years of schooling, where they had done both equally, she had an average of 4.7 out of 6, and he had an average of 4.6 out of 5 points. No, sorry, out of 6. But then they had an oral exam. And at the oral exam, she was flunked. Minkowski gave her a very low score of 5 points when he gave 11 out of 12 to the other 4 students who were all mixed. mentioned that. But the universities in Switzerland were among the rare universities in Europe accepting women. And University of Zurich had graduated 2, maybe 3 women before. Maybe not in physics, that I don't know. I need to research it. So it was really difficult, but it's the time also where they submitted their first paper. And Minerva wrote to Helen, we will send a private copy to Boltzmann to see what he thinks. And I hope he will answer us. Clearly, she implied that this was common work that they were doing. And Albert also wrote in a letter to Minerva. Albert, he wrote that his friend Michele Besso visited his uncle, Professor Young, on my behalf, one of the most influential physicists in Italy. And my friend gave him a copy of our article. So you see, it's clear that both of them refer to this first article on capillary motion that as our article, common work. Why was this article published in the Annalen for Physics under the name of Albert? Was it because Minerva wished to help promote Albert's career? She wanted him to make a name for himself. If he could get a job, he would marry her. So happiness depended on him getting a job and getting a career. And for Minerva, as she will say later, they were one unique entity. For her, they were undistinguishable. You know, it was their work, they were working together. She didn't care so much about others. It was fine if it was signed only with his name. So we have proof of their collaboration, further proof of their collaboration from Albert's own end. In March 91, he returned to Milan, again to probably for the Easter vacation, and to be with his family. And he wrote, how happy and proud I will be when the two of us together will have brought our work on relative motion to a victorious conquest. That's probably the clearest statement we have about how they have collaborated on special relativity. So Minerva is still helping him in his work. For example, those pages are in a handwriting. We see, for example, in the Einstein Museum in Bern, there are lots of their notebooks from school, and you see clearly the handwriting from Minerva. Everything is rather clean, and Albert is anything. But she was often writing his lecture notes for him. And so here, she prepared the lesson. And you can see that it's the first draft, and it's full of corrections and all that. So it was, there are 8 pages of his handwritten notes in that book that are in Minerva's hand. Those are preserved in the Hebraic University in Jerusalem. That's, while passing nearby a massive object like the sun, and that brought him total notoriety, even public notoriety. And that was probably the beginning of the Einstein's myth. Helen Ducasse was Albert's personal secretary from 1928 until his death. And she moved to the USA with him when he fled Nazi Germany in 1933. But Nathan was a close friend of his who also immigrated to flee the Nazi regime, was an economist, and both of them became executors after Einstein's death. These two people did everything they could to hide Minerva's existence. They didn't want that to be known. They legally prevented, that's horrible. They legally prevented their son, Hans Albert, and his wife, Frida, to publish the letters they had found in Minerva's apartment, letters that were published in 1987. So they were blocked until their death, which occurred in 82 and 87. So then they were published in the collected papers of Albert Einstein. Nathan even pushed that to visit Minerva's apartment after her death to clean it up. I don't mean doing the bathroom. But he arrived there mother's wife, and she had found the box containing the letters exchanged by their parents. So that was it. Let's talk today about.
So that gives some idea about Einstein's wife. It is, of course, arguable if how much Einstein's wife helped with Einstein's scientific work, ranging from not a lot to saying she did a lot. Okay. So this is a group of Einstein's friends, and they called themselves the Olympia Academy, and they were kind of Einstein's own version of AMPA. They used to discuss physics and other issues. So, Boskowitz, I'm always promoting Boskowitz. His theory is about point particles, and so from his theory, an ether would be composed of point particles. And if we go back to Newton, he had a corpuscular theory of light, and so that's really a particle theory as well. And I think that Einstein's paper on special relativity was also about dealing with light as point particles, but that gets obscured because of the mistranslation. And this is a quote I found from Bastin and Kilminster in the book The Origin of Discrete Particles in volume 42. And they tell you that Boskowitz, who was in the 18th century, took an important step in the history of the particle concept, in contrast to Newton, who did not analyse the actual impact of particle on one another. Boskowitz, in his book, 1763, thought about forces that might accompany the impacts in a way that was so modern as to make a real change. So Boskowitz was carrying on in the tradition of physics which Newton set up. And I think Einstein was also going from this as well. Because from Einstein's friends, they'd studied Boskowitz theory. So moving now on to the issue of ether with Einstein. Einstein in his 1905 paper says about the ether, it will be proved to be superfluous in as much as the view here to be developed will not require an absolutely stationary space provided with special properties, etc. I'm passing at the moment on querying the translation for that particular phrase. That's because that's from the original mistranslation. He also says unsuccessful attempts to discover any motion of the Earth relative to the light medium suggest that the phenomenon of electrodynamics as well as the mechanics possess no properties corresponding to the idea of absolute rest. Now, really, ether is a type of substance for light waves, and it's also being used for an ether frame or an absolute frame. And so it's not really clear whether he's discarding both concepts of whether he's discarding the concept of there being a substance for light waves and also dismissing the ether frame. But unfortunately, most people to me he's discarding both concepts. Well, Einstein in 1920 brings back the ether, or at least he brings back some type of ether when he gives this quote, recapitulating, we may say that according to the general theory of relativity, space is endowed with physical qualities in this sense, therefore there exists an ether. So it sounds like he's bringing back the ether in general relativity, and all of this is causing confusion. Does he mean there is no ether in the context of special relativity, but there is an ether in the context of the general relativity? And also, does he mean space-time should be the new version of ether? And lots of query questions like this come up. Now, this is a book by Kostro, and he's gone into the issue of what was Einstein meaning by the ether. And according to him, Einstein was giving 3 different models of a new ether. At an elementary level of physics, we're taught such things as what's quoted here from physics tutorial. It says a wave can be described as a disturbance that travels from a medium from one location to another location. And it gets contradictory at a higher level when they start talking about light waves, but then they start telling you there's no medium for light. So it's as they progress from elementary level of physics to a higher level of physics at sort of like degree level, things get very confusing. Now, this is a person called Banish Hoffman, and he collaborated with Einstein, and he published this book in 1983, Relativity and Its Roots. And so this is a quote from him, which is I'm going to criticize. He says, moreover, if light consists of particles, as Einstein had suggested in his paper submitted just 30 weeks before this one, and he's talking about the photoelectric one, I think, the second principle seems absurd. Stone thrown from a speeding train can do far more damage than one thrown from a train at rest. The speed of the particle is not independent of the motion of the object emitting it. And if we take light to consist of particles and assume these particles obey Newton's laws, they will conform to Newtonian relativity and thus automatically account for the null result of the microscopic experiment without recourse to contracting lengths, local time, or Lorentz transformations. Yet, as we've seen, Einstein resisted the temptation to account for the null result in terms of particles of light and simple, familiar Newtonian ideas, and introduced as his second postulate something that was more or less obvious when thought of in terms of waves in an ether. So I'm going to criticize this statement from Hoffman. First off, I would like to say that the idea that his 1905 paper, hold on. Yes, so start again. First off, I would like to say that his 1905 paper on special relativity, where he gets the idea that it's dealing with light, but not as a particle, is a misconception, which one can take from the mistranslation of that paper. And I think of ether as being particle-based, i.e. I think the ether is made out of particles. Also, in the usual translation, Einstein says such things as let a ray of light start for the A time, and that ray can be interpreted as a stream of particles. So the relevant part for this talk on ether is that when Hoffman says his second postulate, something that was more or less obvious when thought in terms of wave and an ether, i.e. really shaking the identification that special relativity was an ether theory, despite what Einstein wrote in 1905. And this is an issue I'm going to deal with again in the following slides. So this is George Spitz. He won a Nobel Prize in physics in 2006 for the discovery of microwave cosmic background radiation, and he seems to be saying there is an ether, and he's treating the cosmic background radiation as, well, an ether frame or an absolute frame. I'm saying that the absolute frame and the ether frame are really much the same idea. So the ether frame is back, but it was the Lorentz theory, which was earlier than Einstein's 1905 theory, that had an ether. Both Lorentz theory and Einstein's theory has Lorentz transformations, and the difference is Lorentz has an ether and Einstein didn't. So are they saying that special relativity is really Lorentz theory? It's a bit of wordplay, and ether is being brought in by stealth. And an example from New Scientist, you often get articles in New Scientist and such things saying, bring back the ether. And it's Brendan Foster writing in this New Scientist in 2019 saying, the luminiferous ether has become a byword for failed ideas. Now it's been revived to explain dark matter and dark energy and potentially unify physics. So get rid of ether was a big mistake, and it's caused a lot of confusion, and we're getting these mysteries of dark matter and dark energy because we've discarded ether. Now, this is a friend of Einstein, it's Max Born, and he's saying about Einstein's paper on special relativity. He says in that paper, Einstein has no references or citations saying from what he was working from, so can give the impression that it springs from Einstein's imagination alone through his thought experiments. But however, he admits, it gives you the impression of a new venture, but that is, of course, I've tried to explain, not true. I.e. he's admitting that Einstein was working from an earlier tradition of physics. And special relativity should really be looked at as fitting into an earlier tradition, which was dealing with such things as ether, etc. And special relativity changed as Einstein changed his mind about such things. So looking now at the twin paradox. The usual way it is presented is an astronaut twin leaves a stay-at-home twin and goes on a round trip in outer space, returning to his home-based twin. Now it's being treated as an idealization that is only motion relative between the twins being considered, so not taking into account the motion leaves such as around the sun and so forth. So you're only considering motion between the twins. So what's usually said is the twin, who's the astronaut, comes back after a journey, and the twin on Earth has aged more than the astronaut twin. There are several things I would like to complain about. I think it's really about clocks being different and not about aging. So I'd say the astronaut's clock would be different to the clock of the person who stayed at home. So this is given a simple situation. Clock of a stay-at-home twin records 10 years passing, and astronaut records 1 year passing. Now, there are things that don't seem to be mentioned by the relativity text and may be deliberately ignored. First, it's not obeying relativity. Laws of physics, the laws of physics, the same in all inertial frames of relativity. If obeying relativity, then each twin would be saying 1 year passed for them and 10 years for the other twin. And they'd be not agreeing that years past the stay-at-home twin and 1 year for the astronaut. Several excuses are given that the astronaut, who is not in an inertial frame, is accelerating while the stay-at-home twin is not accelerating. But that means that there is a preferred frame situation, and many relativists deny preferred frame. I think they've messed up their words. What is a preferred frame but another word for an ether frame? So the stay-at-home twin is being treated as if they're in a preferred ether frame. And a typical example of a bad recent paper dealing with this issue is by this person, Vivian Robinson. And he says, there is no absolute rest reference frame. All motion is relative. And typically does not define what he means by an absolute rest reference frame when he denies it exists. And I think I've defined what it means to me in the example I've just given. It is the frame, the stay-at-home twin is being treated as the absolute rest frame in the situation. And it's simple to deal with this when you've only got 2 frames. When you've got more frames, of course, it becomes more complicated. Next, given a clock of the stay-at-home twin recording 10 years passing, an astronaut clock records 1 year passing, they're not going to agree about light speed, surely, as they measure light speed. The stay-at-home twin says light travels 10 light years in 10 years, while the astro twin says light travels 1 light year in 1 year. So the stay-at-home twin says, according to my frame, light is traveling 10 times faster for you. And astro says, according to my frame, light is traveling 10 slower for you. This is never point really agreeing about light speed being constant. So Einstein's relativity has been misunderstood, and there are several reasons for this. First reason, there's no references in his paper, and so you're not getting a proper connection to the traditional physics he was working from. Second issue, his paper was mistranslated. And third issue, I've got my numbers wrong, his wife probably a major contributor to the theory, and what she should have been, and she's been airbrushed out the history a bit. And the last issue is Einstein changes his mind a lot, and that's not taken into account. So sorry about that. The computer seems to automatically generate the numbers for these bullet points, and I didn't notice it got it wrong. So we don't have to stop there with the mess that has been made with relativity. We could just carry on. So often the route to teaching Einstein's relativity starts with contrasting Galilean transformations versus Lorentz transformations. So it gets presented as Galilean relativity versus special relativity. But that is false. Galilean relativity in that form was not proposed by Galileo, and this is pointed out by K.M. Brown in a paper in 2020. He points out Galileo proposed the principle of relativity, but he did not give the Galilean transformation. As Galileo was the first scientist to hypothesize a universal principle of relativity, but he never proposed nor limited his principle to the so-called Galilean transformation. He proposes what should be called Euclidean space-time transformation. So this Galilean transformations versus Lorentz transformations is false. It's not Galilean relativity. how the problems just get worse. As per this person, Klaus points out, Machians, and these are people that follow the idea of Mach, have several problems to the postulate of the quantity of light C in vacuum, which is the second axiom of special relativity. He says you often find their claim in letters to Einstein and other physicists and other publications, so forth. They demand the complete relativization of all physical concepts. So you're saying that light speed is a constant instead of being relative, then that doesn't make it a relativity theory in their point of view. If it was a relativity theory, it should have light speed c as relative as well, instead of constant. So that's their objection to relativity. So why is there a constant c in relativity theory? Answer is not a relativity theory. So calling it Einstein's theory of relativity theory is a misnomer, as people such as Coleman notes. And he cites Tony Rothman. He says special relativity is probably the greatest misnomer in the history of science. And it's in Tony Rothman's book. And Coleman points out it was not Einstein but Planck who introduced the term relativity theory. That was in 1906, the year following Einstein's miraculous year. Despite Einstein's opposition, the name stuck. Years later, Einstein surrendered. From 1911 onwards, he started to use the term relativity theory himself, but he never felt comfortable with the term, and in his writings always put the words in quotes. So back to this issue of Galilean transformations versus Lorentz transformations. That is not Galilean relativity, and that is not special relativity. So go on to what's Einstein thought experiments, such as what would happen to you on a beam of light. And we look, his group of friends, the Olympia Academy, were studying such ideas as this, as the film Person Demon. And this was published before Einstein. And it was considering the idea of a thought experiment of traveling at the speed of light. So, i.e., there are thought experiments on relativity by Einstein, but there seem to be thought experiments on relativity related issues before Einstein, and they're getting ignored. So we go on to this person, it's John Wheeler. Most people have their understanding of relativity through what is John Wheeler School of Relativity. And one of the persons I'm in contact with, Dr. Lowe, says the Wheeler School has got relativity wrong, and that's his paper there. And this is an example of a problem with general relativity. This is Peter Bergman. In 1942, he wrote a textbook on relativity with Einstein given a foreword to that book. And Bergman did not seem to be in agreement with Einstein about everything about relativity, but they let this dispute out of his earlier book in 1942 to get Einstein's endorsement. And after Einstein died, he wrote a new book on relativity where he changed. So this is an example of the type of revision that happens. And I think the Wheeler School might have gone by what Bergman was saying about relativity. So now we can get on to the issue of semiotics. with this, you have a signifier, and that's pointing to a signified. And what you have is something like a word, and that word or collection of words, and it's pointing to a concept, what that word means. So in the case of Galilean relativity, really, it's not to Galilean relativity. It's not relativity. It's pointing to an Euclidean space-time transformation theory. And special relativity is not pointing to a theory of relativity. It's pointing to a space-time invariance theory. Well, the ether, where it's all very confusing, what is that pointing to now with all the changes made? So I can get on conclusions. Should Einstein's relativity be rigorously defined, be flexible? Seems at the moment to be very flexible, with people saying conflicting things about it, and that flexibility has been its strength in stopping it being overturned. Some people add such things to relativity as ether, preferred frame, etc., when they feel they need to, while others are saying there's no ether, there's no preferred frame, etc. According to Peirce, a sign can never have a definite meaning, for the meaning must be continuously qualified. So people have put in different meanings to terms. So thank you for listening, and I'm citing a few information. Boskowicz's book, Ways, the talk on Boskowicz theory by my friend Professor Dragoslav. Thank you.
Thanks, Roger.
End.
Can you stop sharing a screen, and then we can see everybody?
Stop share.
That's it.
Okay, thanks. Hey.
Okay, so I'm sure there are lots of questions. So who wants to be first?
Nobody, right.
Do you have any comment?
Sorry? Wolfgang.
Roger, do you have any comment about what was wrong with the translation? I read the original German and the English. Thank God my school actually has the Annals of Physics in its library, although they're now gone. But I didn't pick up any major problems. So can you elaborate on that point at all?
Yeah, it's when I read it, I don't find it the same. I've compared two translations of Einstein's relativity from German into English, and I think they're describing different theories. And the words, if you go by the words, you think, well, those words and that translation, that means the maths that's being presented is wrong. So you want to then alter the maths in what's given. But in the other translation, you say, well, maybe the math is right. So you kind of, the way you're translating it is influencing you, what you're going to do with the maths. Okay. And in the mistranslation, it seems to be saying you definitely got to do the math this way, but in the correct translation, it's giving you, no, you don't have to do the math this way. And if you don't do the maths that way, you can, well, change it around and turn it back into Newtonian physics. It's my thought, turn it back into Newtonian physics. I look at Einstein from a tradition which he's working from Newtonian physics. And I'm saying, well, he's still Newtonian physics. It's just he's done the maths in a certain way, but you can just say, well, put it back again to what Newton was doing. So that's how I looking at it. The sort of like the so-say big split between Einstein and Newton's not really there, in my view. And you're bringing back things like the ether. When Einstein says there's no ether, well, Einstein says discard the ether as superfluous. You look at it from a tradition and say, no, it's not superfluous, you've got to add it back again. But the mistranslation is confusing things.
Well, that's often the case, I suppose, yeah.
And also, in the correct translation, it looks more like definitely he's talking about particles of light, the same as what he was doing in the photoelectric paper. And that gets confused in the mistranslation. So it's all wrong. Everything is being taught wrong. I mean, they've kind of gone by the mistranslation and tried to get everything to conform to that. And they've invented these things like Galilean relativity, which Galileo is never talking about. And then they've also invented this thing called special relativity. Well, they shouldn't be really calling it special relativity. They should be calling it space-time invariant theory. And so people reading it, well, people being taught it are thinking they're being taught a relativity theory when it's not a relativity theory. So you've got all these confusions piled on top of the mistranslation. And I think Einstein should have realized this, that everybody was misunderstanding the theory, and he wouldn't have realized it if he was not the sole contributor to the theory. And maybe his wife had a big input to it as well, in which case you've got a perfect storm: mistranslation, Einstein not fully understanding the theory, his wife not being able to give her point of view on the theory, and so forth, and then building more and more mistakes on top of it. Everything is just the mounting of mistakes.
Roger, can I ask what wrong means? Because it seems to me that there are at least two kinds of wrong here. There's a wrong in terms of historical authenticity, which seems to be a big part of your argument. That actually, you know, we're almost behaving as if we're restoring Renaissance paintings and stripping off the varnish and saying, actually, no, this is the authentic thing. But there's also wrong in terms of correctness of the theory.
Mm-hmm.
So I just wonder if you can unpick those two, the authenticity aspect and its wrongness in that sense, and its wrongness in terms of correctness.
Well, you can't really go back to 1905 to undo everything that's been done since then. So you've got a problem of trying to work out what Einstein was actually thinking at the time and whether it's being translated properly into English. And you can't do that anymore. So all these different levels of wrong, it's too late now. You've got a cold case. You're trying to do forensic on something which is too late now.
But people do this.
Well,
you know.
Just to move ahead a little bit, I'm going to be presenting a talk, I guess, in a couple of weeks, and I will be discussing this issue. But just to advertise ahead, I'm going to show that Einstein's is not wrong, but simply introduce two errors that correct each other. So if you accept one, you have to do the other in order to correct it. But that doesn't necessarily mean it's wrong. It's just a different methodology.
Yeah, errors is wrong. If you got errors, then it's wrong.
I think Nicola had a question.
Yeah, I mean, I'm actually going to have to go quite quickly, so I'm sorry. So I just want to say thank you, Roger, because I think it's very, very interesting. You know what you've brought up, and obviously I'm very interested in the fact that, surprise, surprise, that the woman was airbrushed out, but also, I mean, obviously following on from what Mark was saying, that the actual, the whole historical thing, it would be, you know, you could write something up, actually, you know, you're just disentangling, because it is like following the thread through. I mean, maybe obviously just from your, from your talk, And and then I just had this thought that it's a pity that we haven't managed to rope Jeffrey Constable in with his quantum jelly theory, which is a kind of ether type thing, and that would be it would be interesting. But I mean, I've tried to chase him, and I don't know. I don't know what's happened. I mean, that's So yeah. So thank you, and I'm actually going to go now. But I'll look back through the slides. So thank you very much.
Thank you.
Bye now.
Thank you.
Okay, Divyaman.
Yes, I don't want to give feedback, as in like technical feedback. But, I just had a simple question about the different spellings of ether. And like, you know, if you wanted to mark a distinction between the two, or like trace them, or because with the AE versus the E in the spelling of ether, and I thought you switched back and forth between them, but I was just wondering if you wanted to talk about it.
There's been a lot of ether theories, which is basically a medium for light waves. There've been lots of theories trying to come up for that, but ether is also a chemical. And so sometimes people distinguish between ether as a chemical and ether as the light medium. And so I generally usually put A in front of the word ether to mean the luminiferous ether, as opposed to the chemical ether.
It's also British and American.
Is it? Yeah.
I think American doesn't have the A so much. British has the A more.
Yeah.
In principle, they'll both probably use them. Yeah.
Yep. Of course.
Could I ask something?
Yeah.
We'll lose next, Peter,
Okay.
then Peter Marcer, and then you.
I just wanted to bring up a point that Einstein's whole thing about the constancy of the speed of light pivots around his understanding that he wants to frame electromagnetic theory so that the speed of light, which comes out the same in constantly moving reference frames, will be understood from his point of view.
Yeah.
So that's the reason constancy of the speed of light is in there.
Yeah. But that's sort of like, that's it in inertial frames. I think if you're measuring the speed of light relative to your inertial frame, then it's supposed to come out as C. But then what happens when you've got a non-inertial frame? You're measuring your speed of light relative to a non-inertial frame, and what's that going to supposed to be? And also, if you measure the speed of light relative to your frame as C, are you then going to automatically say that the other person should be getting C as well? And I think all those things are not properly explained anywhere. It's not being properly clarified.
Okay. Peter Marcer, then Peter Rowlands, and then Mike Horner. Peter, you have to unmute. There we are.
Yeah. I would have thought that was very interesting to hear about Einstein's wife, but surely it is just something to do with what is still called in modern parlance Me Too.
Yeah.
That men are highly prejudiced against giving equal status to women.
Yeah.
And it's still, as we know, very common, very common today.
Yeah.
I would have thought the thing that really settled these arguments was the point that I thought Mark was making, is experiment. If we do the experiments, as must happen, say for example, in the design of the Large Hadron Collider, we must know that what place special relativity is incorporated into the design. And of course, the design on the Large Hadron Collider actually works. Similarly, on Earth, the thing that you all have on your phones is GPS, and if general relativity was not actually correct, then we wouldn't get the we wouldn't get the right results on our GPS systems. It just has to be that way, and I'm not really well. In fact, one of the people who used to hamper was the of speculations in science and technology, and he told us that about 2/3 of the papers submitted to that journal in the long distant past were always about this question of what special relativity actually meant. But I would have thought, say, it was suggested it's a question of what is correct experimental.
Yeah, but I've argued with people about relativity, and some people will say there's no ether, and some people will say there is an ether. So you've got an understanding of relativity. Some people understand it as having ether, and some people understand it as not having ether. So you've got this conflict in understanding. And so when you go to something like CERN, when they're doing their experiments, what are these physicists doing? Are they working from a belief that there's an ether frame, or are they sort of saying there's no ether frame? And so you've got this conflict in what are they thinking versus what is being taught. And what is being taught is there's no ether.
I think your paper was great because it gave us the history of this question, which, as you say, to some extent is still actually ongoing, and I found it extremely enlightening in that particular sense.
Yeah. Great. Okay, Peter Rowlands, Mike Horner, then Lou again.
Yeah, I've got two quick questions. Well, the first is more a comment. This Galilean transformation not being due to Galileo. Now, there is an old argument for that, in the sense that Galileo never talked about straight line motion in his work on this. He always talked about motion in a circle. And so in principle, then, that VT doesn't apply because it's a straight line motion. Is that the reason?
I don't know. It's sort of like Galileo said his things, and people after him have to revise it a bit. And it's never...
Yeah, that's correct, because he doesn't do straight line motion. So in principle, it is not actually the Galilean transformation we now use, which only got that name in the early 1900s.
Yeah. So what we
the
call
second thing is, I'm interested in what Bergman said about light could change direction and not speed. But then that's surely fairly obvious from the point of view that you can get gravitational deflection of light, and it must be changing direction.
Go back to the Galileo. First of all, Galileo issue. The Galileo relativity is done by somebody other than Galileo, so that's the problem with that. If you're being taught Galilean relativity, you think you're being taught something which Galileo was talking about when you're not.
He did talk about relative motion. Yeah, he talked about that on the surface of the Earth, but the Earth's surface is curved, and therefore, strictly speaking, it doesn't apply minus VT. I understand that.
And with the gravity bit, I've argued with
what Bergman said in 1968. That is that. I would have thought that's obvious that it can't change it can change direction because you've got gravitational deflection.
Yeah, yeah. So I think with the general relativity, it's about reference frames, and if you're choosing some reference frames, you've got inertial, non-inertial, and so forth, and then you bring in proper reference frames, and so sometimes they want to talk about frames where the speed of light is always constant. And
so you're talking about general relativity now, not about
special. So they're bringing in extra terms, and so
you have a closed space-time.
Then they don't want to talk about frames where the speed of light isn't constant. So they just want to concentrate on the frames where it is constant, where it's what they call it local light speed, local frames.
That's never fully worked, by the way, but no
yeah, but they try to fiddle it around.
Yeah.
That sort of way, you kind of like local frames and local light speed, and so that's kind of the fiddle going on there. It's more complications on top of it. Go back to Einstein. He seems to be saying light speed is variable in general relativity in some frames reference. He seems to be saying that.
Okay. Okay, Mike Horner and then Lou.
Roger, first comment. Thank you very much for attempting to do some corrections of things in the past.
Yeah.
But going on what Mark said, then there is a sort of more modern view.
Well, yeah.
In your talk, you mentioned purse and you implied meaning and stuff like that. I think the modern idea of meaning is that there is a collection of people who share meaning, and in those new, shall we say, descriptions, the position of the observer who's asking the questions about meaning and all that, they are unfortunately quite complicated. If you've managed to fiddle around with laws of form and the differences and all that stuff, you get into a rat hole there.
Yeah.
But if you say, just for temporary thinking, that the emerging new version AMPER or a subset of AMPER is about, then if you look at my work and Job's work, both of them have got new views of space-time. So in that emerging thing, which I could not possibly defend, but it begins with philosophy and it throws out the Lord of the excluded middle and stuff like that, there are no mentions of ether or space-time in the normal sense. Neither is there a word phlogiston and entering into the equation. You see what I mean? Throw it out. If you're looking forward, we don't need general relativity. It's as ancient as phlogiston. Get with what Joe Brenner and Mike Manthey is telling us and use the mathematics, which Lou will explain to us one day.
Yeah.
Okay. Roger, do you want to say something to that? Or
yeah. The problem there is that with Einstein, he sort of like started changing the meaning of words. You got momentum and maths and all that meaning certain things with Newton, and then Einstein's kind of putting in new things like relativistic momentum and relativistic mass, and so you're changing the meaning of the physical terms. It's sort of like what you're talking about now. You're talking about Joe Brannan and that, they seem to be changing the meaning of words again. So it's more wordplay. It's sort of like Einstein did some wordplay, changed some word terms, and now somebody else is building on top of that and doing some more. But sort of like you still go back to what's being taught at university about relativity, and that's still confused about how it connects to Newton. It's still a confused mess from that. So you're just building more and more confusion on top by playing around with your ideas about throwing away the idea of law excluding middle and so forth.
I mean, there's a lot to say about universities there, but maybe we shouldn't go there. Lou.
Yeah.
I wanted to remark that this discussion about the ether there's a very interesting discussion of it in this book by Frank Wilczek. The title of the book is The Lightness of Being. So a very nice book about modern physics that Wilczek wrote. You may be familiar with it. But Wilczek makes the point that Einstein's first foray into quantum theory was the photoelectric effect, where he postulated that photons were particulate. And then he goes on to point out that, I'll just read this to you.
Yeah.
I'm not sure that Einstein was ever convinced about the electromagnetic ether. One of his greatest strengths as a theoretical physicist could also be a weakness, his stubbornness. Stubbornness served him well when he insisted on resolving the contradictions between the two relativities, mechanical versus electromagnetic, in favor of the latter. Again, when he insisted on taking Planck's ideas seriously, extending them, despite their conflict with existing theory. And he goes on along those lines and points out that by the time Einstein got the general relativity theory, he essentially forced himself back into an ether point of view in the sense of manifold and the metric and the field, the global field, but that he remained uncomfortable with that. And in fact, you can find other passages where he wishes he could make a discrete theory, or he wishes that he could see it all in terms of certain kinds of singularities of space-time. So this debate is going on not just outside of Einstein, but within Einstein throughout his life.
Yeah. I would have liked to shown a video clip of Wilczek, and in the video clip I got of him, he's saying that the ether exists. And that is sort of the problem we've got, is some physicists are saying there's no ether and there's other physicists saying there isn't ether. And it's just an ongoing argument.
Roger, any extra resources and stuff, when I post your video around, maybe if you reply to that and post any links to YouTube on the AMPA chat, that would be really good.
I'll write the title of Wilczek's book in the chat.
Okay, thank you, Luke. John Hyatt, did you move your hand to ask a question, or did no, that's fine. Okay. Anybody else? Any questions? Right, John Williamson.
That's a very interesting book by Ludwig Kostrow about Einstein's changing views about the luminiferous ether and about the ether. Well, it contains more than that, but that's one of the themes of the book, how it evolved from 1905 through 1914 through 1920 to the later parts of his life, which I'd recommend to anybody to have a look at. Kostrow, Polish chap, Ludwig Kostrow.
Yeah.
Einstein.
Okay.
Yeah.
How do you spell Kostrow?
Yeah.
I'll put it up on the chat, okay?
Okay, thanks.
Yeah. So, it's part of this argument about ether. There are physics, I say, teaching people about how relativity, and one I looked at recently, explaining that relativity got rid of the ether theory. And I comment in one of the chat things on it that say no, ether still exists. It's all right. It's the teaching method. They're still teaching the method. Oh, relativity, and it's got rid of the ether. And then you've still got people who are saying the ether exists, like Wilczek and so forth. And Kostrow is also brings back the fact that Einstein was still having the ether. So it's all sort of what's been taught to physicists at an early time at university is all getting. They're not giving them the controversy over this issue. They're just being taught something dumbed down for them.
Okay, Peter, and then Wolfgang.
I was just going to say, has there ever been a bigger straw man in the history of science than the ether?
Yeah.
It's the perfect straw man for people to attack. It doesn't mean a damn thing. You know, you can make it anything you want it to mean. And You know, there's a million versions of it. What about vacuum that we use today? Is that ether? It's just meaningless.
With so many versions of ether, it's difficult to disprove every version. You've got 100 different versions of ether.
It doesn't need to disprove anything. There's no need to prove or disprove. You just develop a theory.
Yeah.
Some people call bits of it an ether. Some people don't. It's a straw man, the whole thing.
Yeah, but
when unnecessary to say we've got rid of it or we've got it.
When they teach relativity in the video I was watching, they sort of like given a definite statement that they got rid of the ether.
Yeah.
So that is false. They can't really say that if there's hundreds of different versions of ether. They're just saying they should be really saying that we're not using the ether concept anymore because it's ambiguous.
Okay, Wolfgang, then Lou.
They're not saying that.
Wolfgang?
Okay. Unmute. Okay. This is a lot of controversy about semantics and what someone thought and what other people thought. What do you think about the equations themselves? My question would be that much of this is dependent on the use of phases to measure distances as well as to measure time. But there's also the particle thing. So I've read, and I forgot, I think it's Solari or someone wrote a book where, for example, he would coordinate reference frames not with phase signals, but I think he had a thought experiment where we take a fax copy of a clock dial and send that to the other reference frame, and then, you know, nothing changes in the fax. I mean, it's a piece of paper. You know, so a lot of it depends on what methodology used to define the reference frames in the first place. And so I guess my question is, given all the controversy about definition of terms and what somebody thought, what do you think about the actual equations? As far as I know, the time delay is fairly well understood and used, but the space part is very questionable, even by experiments.
Yeah, well, I just stuck on the time dilation thing. The way that they teach the maths is usually they give you the Pythagorean theorem, where you've got light bouncing between mirrors as they move. You end up Pythagorean theorem. It's sort of like, it's very dubious to me that they suddenly introduced time being different between the two observers. You could, Pythagorean theorem, you can just treat that within linear physics from the assumption that both observers have got universal time the same. So suddenly they want to say, well, no, you got Pythagorean theorem, and you're going to assume their clocks are different. And it's sort of like, it doesn't, they're plugging into the maths the assumption the time's going to be different when it doesn't really look like they need to do that. Why suddenly make that change from how Newton would be dealing with the Pythagorean theorem? When they teach relativity, they don't really go into sufficient detail to explain the sort of like fiddles they are doing with the maths, to go from one way of talking about it to the other way of talking about it.
Lou?
Well, you know, we teach it to ourselves, at least. When we teach it to ourselves, at least, we make it as clear as possible what assumptions we're making.
Yeah.
And making a lot of assumptions. I'm just talking about ordinary special relativity. The basic assumption that you make is that the three-dimensional space is local and Euclidean, and that the light is traveling in it, but that the light satisfies Einstein's postulates.
Yeah.
Then you get to use the Pythagorean theorem if you want to. And you get to use those things, and you make the conclusions that you do, given Einstein's postulates. Yeah. And it's logical. It's also very unintuitive in the end. But then you have to ask yourself, well, am I really going to stay there, or do I want to go into a deeper set of assumptions? And of course, people have, since Einstein's time, when he did it the way I just described, more or less, tried to investigate lots of other underlying assumptions about the background space, and this goes on. And so there is this continual investigation of the modeling about the background space, or perhaps the saying that there should be no background space. Instead of assuming, and you can't anymore assume, that there is just some unknown liquid luminiferous ether. You can't do that. You can't just say there's something or other that behaves like a fluid that's elastic. You've got to make the model more explicit in these times. And so people try, and they're still trying to make background space models of different kinds. An example of a nice extreme one is Roger Penrose's attempt by spin networks to create a background process model for space-time itself. And this kind of thing continues. So this is an ongoing investigation. And Einstein's original words are not written in stone. End of rant.
Yeah. Okay. Thanks. No. When they try teaching relativity to me, I'm a more awkward person, and they usually teach the two assumptions of relativity, and to me they're not clearly explained as to what those assumptions mean. They start saying, first one, principle of relativity, the laws of physics the same for all observers, but they're not saying, oh, this is, most of the time they're not saying, is this only for inertial observers, or is it both inertial observers and non-inertial observers? And then they bring in, well, the speed of light is a constant, is a law of physics. It's sort of like, how do they make that jump? It's sort of like, it's a jump, and it's sort of like, well, where's that coming from? You're assuming that.
Of course you find it as a student. It seems really strange.
Yeah.
And you have to understand the background, which is that the speed of light is calculated out of electromagnetic theory, and therefore independent of the inertial frame. And Einstein is setting up a theory which shows what the consequences of that are. And of course, you're assuming all your classical ideas except one, and seeing what happens when you do that derivation.
But as far as I'm concerned, they're not properly contrasting how you would do it before Einstein with how you do it after Einstein. And sort of like, well, what does the math look like before assuming that, and what does the math look like after assuming that? And I say, well, if you assume that you've got universal time, the equation, you can change the equations around a bit, and you say, well, this is what it looks like, and it's not connected to Galilean relativity at all. What they're saying is Galilean relativity is not Galilean relativity. That is just a diversion. So you've got some equations with universal time, and you've got some equations with the speed of light is constant, and they're not contrasting those two types of equations and telling you why you're going with one set of equations as opposed to another set of equations.
Well, instead, I mean, I wouldn't know what convinces you. You know, I mean, like some geometric thought experiment is one that convinced me as a student, or maybe it was later on, where you have the moving train and you look at the photon, and on the train it's going back and forth between two mirrors in a vertical tube. But from the observer's point of view, it's going up the hypotenuse of a right triangle. And then you compare using the Pythagorean theorem, and out come the relativistic transformations. So the derivation at the mathematical level is crystal clear. But then of course, when you're first learning it, you resist this thing. It doesn't seem right. And you're probably right that it doesn't seem right, that you'd like to understand it in a deeper way than that.
I've resisted it all the time. So I've resisted it. You don't have to do the maths the way that they're presenting to you for the Pythagorean theorem, you're putting down speed as constant into that Pythagorean theorem, and I've resisted it. No, you don't have to do that. You can come up with this other bit of maths with universal time, and they're not teaching you, well, why are we going to jump from that bit of maths with universal time to that bit of maths with constant light speed? They're not teaching you that. Instead, they've set you on a diversion with Galilean.
This is like finding.
Yeah, they tell you this Galilean relativity. They set you off and say this is relativity according to Galileo. Then you find out it's not, and so it's not nothing to do with what Galileo was talking about. So they're just completely set you off on a red herring. They've not.
But you see, the problem is, how do you understand? Shows it to you, but you could ask, how do I understand it? In mathematics, there are situations where we come to an understanding. Bolyai and those people, they found non-Euclidean geometries, but they didn't have models. Then we found models, curved surfaces, Gauss, and so on, and we begin to understand exactly what's going on with non-Euclidean geometry. Something similar might be possible for the intuition with relativity, but I haven't seen it yet.
The
question is, when will your intuition rest? But that is not a mistake of the person who made the discovery. That's just it's your own unrest, which is creative.
Yeah. So I'm an awkward student. So if you're teaching me it, well, you've lied to me pretty much about the Galilean relativity bit, and this special relativity, where you've lied to call it relativity, it's really a space-time invariant theory. So you've tried to confuse me as to what you're talking about. So you haven't really presented to me the maths properly as to how you're really switching from what Newton's dealing with to what Einstein's dealing with. It's not been presented properly with citations and references of who's done what. It's suddenly just a big jump. And it's semiotics and semantics and everything is all being messed up.
Okay, John Williamson.
I think the reference is Maxwell. And I think Einstein's almost irrelevant here. When you're talking about what Maxwell discovered, Maxwell has a set of linear equations. Those linear equations relate the rate of change of the way in which an electromagnetic field evolves. Electromagnetic field evolution has parameters. Those parameters, epsilon and mu and c. There are 3 there, of which 2 are independent. Yeah. So you can choose those 2. Now, imagine you forget about c and you just look at epsilon and mu, and you look at the local epsilon and mu.
Yeah.
That local epsilon and mu can vary, but they give rise to a speed of light, which is 1 over square root of epsilon and mu.
Yeah.
Now, what you're talking about here is you're talking about something which is the kind of thing which, when you move to the way that relativity is taught, you're talking about the synchronization of clocks, and they're synchronized with light signals. Now, if you look at this properly and have a look at the way that this works, it means that everything is related to the scale of rulers and clocks through epsilon and mu. Now, insofar as those things can change locally, it then doesn't matter what they are, you still measure the same thing. And what you measure is the same thing. So if you then look at the speed of light and you relate it to that thing, that speed of light is whatever it is. And that size is something which tells you what the scale of rulers and clocks are. Now, however that varies, you don't give a shit, because whatever happens, you're relating it to that size scale in terms of light. And then what you measure in terms of c, which is simply 1 over square root of epsilon and mu, is always the same. So you do not know, and you cannot know, and it's not worth talking about what this constancy of the speed of light means, because it is something which is a given within this set of simple linear differential equations. Given that those are true, then the speed of light being constant follows. End of story.
Yeah. When they teach relativity,
no, they are not they are we. We are those people who teach relativity. So who is they? No, don't talk to they, talk to me.
All the people that have been teaching relativity, they seem to want to go.
Yeah, but I'm one of them. So don't talk about those people. Talk about me people.
Are you telling me you're teaching it from Maxwell's theory? I haven't seen it.
No, I'm talking about having taught it to students. Having, you know, I'm a university lecturer. I've taught it. I am teaching it. I am they. They are me. They are us.
I haven't seen an approach where they start from Maxwell's theory and then get special edited.
Well, I've just laid one out, and of course, Einstein himself said that he found the primacy of Maxwell's equations was important, which you've stated yourself, and that is so. But if you do that, you're talking about a speed of light which is derived from the parameters, which you then can measure, because the measurement scale itself is given by the parameters of the theory. So then one's talking about nothing, because one's talking about something which is relative.
I haven't seen a talk.
No, well, I'm just giving you
on how they get from Maxwell to Einstein. But what I've seen, they try to deal with Newton.
Well, all you need to do, I have it, for example, in my 2019 paper. I also give it in the talk I gave last Thursday. So if you want to look at that, it's there.
Yeah. No, if you're starting from Maxwell, then Maxwell has an ether, and so I would think that Maxwell was thinking in terms that he's got a his theory.
It doesn't matter whether there's an ether or not. What matters is that the equation, no, it doesn't, because the equations sit apart from that. If the equations are true, whether or not there is an ether, and in fact, the ether is just, you see, what you say there is an ether, you're saying there is something which is separate from the things which are defining the parameters of your theory.
Mm-hmm.
Now you can do that. You can say, there's my theory. My theory has these numbers. Mm-hmm. But on the other hand, there's also, apart from that, an ether.
Mm-hmm.
Then you're inventing something extra on top of the parameters of the ether.
Mm-hmm.
So you can't do that, because you can't say, look, I've got all this stuff. I've got these numbers here, these two, and I've also got these two, which are different, or are they the same?
No.
You can do that. You only have two numbers. You don't have four. So yeah, you're talking about the nature of what's defining reality. And the trouble is, you're trapped in, you are part of it. Look outside of it and say, there is this and there is this, and these two are not the same, because there are only two, there are not four.
But anyway, if you were starting from Maxwell's theory, you would be having the terms which he's talking about, and he is talking about ether and things, and you say, well, suddenly from his context, he would not be he'd be wanting to get his theory to conform to Newtonian physics.
They're not talking.
You wouldn't be abandoning it. So you suddenly.
I'm talking about. I'm not talking about that. I'm talking about. You see, what Maxwell did or didn't think, we can't know, because he's not with us anymore. But what Einstein did or didn't.
But he's not coming up with saying, we're going to abandon Newton. He's not writing.
No, absolutely not. No, he's not.
So his starting to be, you've got Newton, and so he would be trying to get his theory to conform to Newton. And so
you have to realise that whenever
you'd be asking, why are you suddenly changing from Newton to something else?
Are you
saying
that you think Maxwell did nothing over and above what Newton did?
Well, he's not saying about abandoning any of new stuff. He's
no, he's not.
He's still working within Newton. It's not until you get to Einstein and that you're talking about away from Newton.
But each one of these great people introduced something new.
Yeah.
Otherwise, something new was not introduced.
Yeah.
Do you accept that? Do you accept there was anything new in what Einstein did?
Yeah.
There was, that it has to be different to what had gone before, or not?
Yeah. Einstein, he has read Maxwell.
Of course he has. But does
but
he?
He's not citing. He's once again the problem with him. He's not citing references from what parts of Maxwell he's going by.
But look, the thing is that when people do something new is done. When people do something new is done. One has to distinguish what that new thing is.
Yeah.
And if Maxwell was not beyond Newton, then Maxwell wasn't beyond Newton, and Maxwell did nothing. If Einstein wasn't beyond Maxwell, then Einstein was not new, and Einstein did nothing. But there are new things that have been brought in by each of these people.
Yeah.
New understanding, new depths. So, but what Maxwell was doing, what Einstein was doing, is just saying, look, you can look at these things in terms of what we think in terms of Euclidean space and so forth, or you can look at them in terms of what taking on all of the consequences of what Maxwell was saying. And in a sense, for special relativity, that's what Newton was doing. Now, in that, Einstein is saying, look, here I subsume myself to Maxwell. And the consequences of taking all of that on board are that this is the case. So were we to take that on board, then this would be the case. And making that kind of distinction for the nature of space and time is a contribution that Einstein made, one of the many contributions that Einstein made, which we now call special relativity. But one can understand that, but it is a new thing that he's bringing in just here, as Maxwell was bringing a new thing out over and above Newton. Now, in each step, if it's properly done, and if the preceding theory was a good approximation of reality, then perhaps it's not a very big step, but it still is a step, which is progress. And in both of these cases, Maxwell's and Einstein's cases, there was actually some progress.
Yeah.
Well, isn't the real question that Newton assumed that there was a space, and Maxwell assumed that in that space there are charges and fields. Therefore, the charges and fields, when taken separately, have their own identity, but the question is there some additional space in which the electromagnetic phenomena happen?
That's exactly the question, Wolf, and that's absolutely correct. So the question is there both a space in which that happens and the of that space or not? So if one's looking for operator and one's looking for the simplest thing, then one should say there aren't two, there is just one. And that one is unknowable because we're part of it, but it has properties. So, and in a sense, that's what Einstein's doing. He's simplifying the situation. He's taking the number of total parameters down.
He's not saying what he's doing. If you start from...
No, forget about Einstein.
No.
We are here. We can say what we are doing. We're alive. We can explain what we're doing.
Yeah. But Einstein's not giving sufficient details about what he's doing. You've got, sometimes it's explained that Einstein had the choice of either changing Maxwell's theory or changing Newton.
Look,
and he went with changing Newton.
What Lou said is what Einstein did. Einstein was never sure. He was never 100% certain. When Einstein said something, he wasn't God.
Yeah.
He didn't say something which was then written in stone. He was struggling and thinking about how things worked. He was trying to understand as best he could with the else
that makes
ever done how stuff worked.
Yeah, it's ambiguous because he changes his mind, and so one minute you got him saying, "Oh, this ether is purposeless." That's 1905.
Roger, have you ever changed your mind?
Yeah. So I don't change my mind ever.
You don't change your mind ever?
No, I'm always right. I just want to think that it's always right.
Well, fair
so,
enough. We're always right.
But with Einstein, they say one of his virtues is that he was ready to change his mind.
Of course he was. Because
so that is supposed to be a big virtue, that when he's presented with new evidence, he'll change his mind.
Of course.
It's one of the problems of being...
It's ambiguous.
You change your mind. As a theoretical physicist, what you do is you say, what if it's this or this?
Yeah.
And you continuously have two or three things in your mind at the same time. Yeah. And especially, is space an arena or is it an illusion?
But you look at what he's saying, and it's ambiguous, along with it being mistranslated.
It's far worse than that.
So,
what he is saying, you would look at what he has said. What he has said in 1905, in 1914, in 1916, in 1925, in 1940. They weren't just ambiguous, they were seriously different. Why? Because great minds do not think alike. Great minds think differently.
It's ambiguous.
And he thought differently all the time.
It's ambiguous in the sense of, is he talking about ether?
It's different. It's completely different.
Talking about ether not existing in the context of inertial frames? Or is he talking about ether doesn't
he was thinking, okay, what if... No, you don't get this. The thing is that Einstein wasn't thinking... Einstein was a genius. He didn't think one thing. Can you imagine? Einstein had his thought. Einstein's thought, ooh, that's it. That's my one thought. That's rubbish. He was a genius. He thought lots of different things.
Yeah.
So And the things didn't necessarily agree. You know, Einstein didn't agree with Einstein. Of course not. He's sitting there questioning himself, having a look.
That makes it, when Einstein doesn't agree with Einstein, that makes it ambiguous, because you can start quoting one Einstein is saying such a thing, and the other Einstein is saying something else. So you could ambiguity.
Well, that's right. But what I'm saying is, it's worse than ambiguous. It's not ambiguous. It's multibiguous.
Yeah.
It's multibiguous. Forget about it.
You got loads of different theories springing from nowhere.
Right.
You've got Einstein saying one thing.
Well, that's right. I mean, he's making it up.
Else. Well, there's another theory.
Up, you know, make it up.
You've got loads of
that's
theories.
Right. You make it all up.
Yeah, you make it all up. Yeah.
We've got a new word, so I'm ready. You know, this is great. Lou's got a question. It just seems to me that being dead, one of the principal disadvantages of being dead is you can't change your mind. But anyway, Lou.
Not anymore.
Yeah. There's a problem in the background here, which I want to articulate. And that goes all the way back to Maxwell. You remember Maxwell wanted to make a mechanical model for electromagnetism, and he gave it a good try, and it didn't work. And nobody since could do it either. That's the old hidden variables problem, if you think of it in modern terms. He wanted to do it. He wanted to get that theory about the electromagnetic waves to be as palpable as the way waves patterns work in a fluid, in water. And he could not do it. Mm-hmm. And so the theory became abstract. And the ether disappeared at that point. That's when the ether disappeared, if you want to know when it disappeared. It disappeared at the failure of that model.
It did, but that model was quaternionic, and he was thinking quaternions. It was damn close.
Yeah.
Very, very close.
We'll get back, right.
For a long time. I think, you know, those quaternions were pretty spectacular, and it was lovely. Read the original stuff. It's fantastic. So he was so close, but he was in 3D, not 4D, and well, that came later. It's time to fix it.
I don't think you got a reference where Maxwell says discard the ether. You got it from Einstein, but not from Maxwell. So Maxwell was probably still struggling with the ether while he was still alive.
It was worse than you think. I mean, Maxwell was thinking about cogs and gears and wheels within wheels.
Yeah.
He was thinking about stuff in 3D. He was thinking not about a luminiferous ether, which was carrying space and time, but something which was more concrete, just as you said. Look at it; it's beautiful. It's beautiful.
I've seen it, yeah.
But what's the difference between the word ether and the word electromagnetic fields? I mean, are we talking about something really different? I think Maxwell we could always throw out ether, but we still have the fields. The fields are an ether in a sense. The fields are the medium in which
the differences between how you understand how waves work in water, because you have a substrate and you think of the molecules moving in their patterns and the waves coming out. You have a substrate in which you understand where the waves come from and what they do. And you don't have that, and the ether was supposed to give you that.
But we're talking about words. I mean, what we have is a substrate.
No, I'm not talking about words.
Field.
I'm not talking about words. I'm talking about the non-existence of a hidden variables model for electromagnetism. It doesn't exist. The ether doesn't exist in that sense.
That's right.
You could want one.
You can want it, but it's an extra thing.
So we moderns make a mistake and we say, well, the ether is just the manifold. It's just whatever background model that we produce. But that isn't what people had in mind for the ether.
That's not right. No, but look, what is really happening here is that you have a set of equations. You have something which is describing, which is a parallel or not with reality, which you're trying to make up. And if you look at the way that Einstein's view of the ether changed, it went from 1905 no ether, then it went general relativity. There's something happening here, and I know there's a variation in effective velocity happening here. He then tried calling it the ether again, but then later he moved to a different word, which he called the total field. So in his later life, he was calling the same thing the total field. So this is the background field of the universe, which is more like what Peter's talking about, or what I'm talking about when you're talking about a reflection or inversion of something, which is which is the other half of whatever the interaction is, if you have an interaction at a point, which is the observer. In your terms, Wolf, in terms of looking at the observer is sitting here and now at the pinnacle of existence, at the cutting edge of reality for each one of us. But that interaction is happening with a bunch of things which are in our past. Now that thing is, if you like, Einstein's total field. That's the ether. But it's the field. It's nothing new. It's nothing extra on top of that, because you've already got all of that. And you mustn't try and duplicate it. You mustn't try and say it is this and it is that, because it can't be two things. It can only be one thing. And if it's one thing and you're one thing, your mathematics already contains a four-dimensional space-time, then it only contains it once. It doesn't contain it twice. And it doesn't contain it three times. It doesn't have a 3D1 and a 4D1 and the base stuff of which this stuff is created, the nature of space and time, the total field, the ether then. So you mustn't start concatenating this stuff and saying, you got 4 of these, and then those 4 things exist in 4 of these, and we've got 8 of those, and we've got 16 of these, and we've got another, and then we've got SU3, and we've got another SU3, SU3 of color, SU3 of flavor. Oh yes, and then we've got SU2, and we've got U1, and you have a dog's breakfast, which is the current situation, pretty much. We have to fix that by looking very clearly at what is and what do you need and what's extraneous to all this shit. So and the trouble is that you're looking at that from within the shit. You're deep in the nature of space, time, and reality because you're part of it. Mm-hmm. So it's, you're only looking at shadows, and it's. So
I'm going to.
Yeah.
Sorry, John.
I agree with that, but the question I have is real simple. Is some people believe that a charge generates a field throughout space, which is its field equivalent out there somewhere.
Yeah.
And light waves that field. So isn't in that sense the electric magnetic field something like the ether? And are we not just talking about different words?
Yeah.
I mean,
no, we're not just talking about different
words.
Lou
says that there's something completely different that was meant. Well, okay, but what is the difference between charge field and an ether?
Okay, right. Let me try and say it very specifically. If you're looking at charge, charge is a vector quantity. Charge is part of a 4-vector quantity. It's part of a current charge 4-vector. Actually, it's a bit more complicated than that, but not much more. So it's a charge. So we're talking about something which is an odd quantity. If you're talking about field, the field that it generates, that's an even quantity. That's a bivector quantity. So look, the two things are very intimately connected, but you can't count them twice, because the point is that because everything is in a process of change, that you have an evolution of things, that those fundamental equations of change are first order equations. And a first order equation relates an odd thing to an even thing, which means they're really the same thing. You can't have one without the other, because each one is continuously transforming from one into the other. So you can't have the one without the other, or the other without the one. So the charge is the odd part, and the field is the even part of the different sides of the same coin. They really are the same thing. You mustn't count them twice. So you have a charge, it generates a field. A field, a divergent field, a divergence of E is non-zero, is a charge. So the two things are related by a differential equation. That differential equation is something which is describing some sort of process, some dynamics. And that dynamics is set up by a series of constraints. And those constraints define the way that the universe, not the constraints of our maths, which is some shitty child's copy of what's happening in reality, but in reality, there is something which is dynamical, which is generating charge, which is generating field from charge. Now, you can look at things, and Al Kracklauer, our friend Al, was very strong on this. You can really get most of what you need by saying that there is no field, there's just charge. And there's just there are just the equations that have a look at how charge acts in the past. So, and to a very, very good approximation, that's true. But you see, the point is that the two things are not really different. They're really a dynamical, because they're a set of constraints which describe how the universe works, they're very strongly related to one another. You can't have one without the other. So it's not they're two different things, it's they're the same thing. In reality, I mean, whatever that is.
That's what I'm saying, is there two
Yeah, I
aspects
think
of the
it
same
is.
thing. We've given it two names. Now, where there is a big difference is if we consider charges and magnetic fields and all that stuff as then one might introduce a mass field equivalent and consider that there is some relationship between where all the electromagnetic charges are in some sort of field that has the mass inertial component. So one could consider there to be two kinds of fields or field parameters. And then call one the ether of the other, you know, some combination like that.
I think as you start to call things other things which are different from the things you've already called something, one's introducing, in a sense, a distinction between things that should not be distinguished between, because they are the same thing. Now, you and I have just agreed that charge and field are related to one another. But I think that also field and mass are related to one another, because I think that field and mass, the masses, their even components, should all be related. There are 8 of them. And that current, and by current I mean both current and charge, and spin and source should be related. There are 8 of those too. So in my theory, there are 2 pairs of 8, one odd pair, one odd set, one even set. But the odd set defines the even, and the even set defines the odd set. So although there are 16, there are really only 8, because you have 8 constraint equations. But then you have more constraint equations, like the linearity constraints, the conservation of energy constraints, in other words, and you end up with there being only one thing, because you end up with 15 constraints on 16 things. And the one thing that you end up with is, well, you can call it what you like. I call it root energy. So, but in order to really understand what's going on, you need to get that full set of constraint equations, and then have something where your theory precisely parallels reality. Now, that's the solution to Hilbert's 6th problem, and that has not yet been discovered. So, but nonetheless, I think our job as physicists is to move towards that solution of Hilbert's 6th, one of the unsolved set of Hilbert's wonderful maths problems.
Okay. On the issue of total field and so forth, Einstein did not present a unified field theory, which he did not keep changing. He kept changing his mind about things, so he didn't present a final unified field theory. So you've got ambiguity again from that. You're talking about development from what Einstein has done and trying to carry on his process. Where
That's
he's
right.
changing.
You have to realize Einstein wasn't the only one.
You're going back to the original source, 1905, and there's already ambiguity in the mistranslation.
Roger, of course there's ambiguity. There's more than ambiguity. There's multiguity. Look, the thing is, Einstein didn't do that, but you know, everybody else didn't do that too. He wasn't the only one who didn't do it. So you can't blame him for not having a total field theory if everything works. He has been the most influential physicist and scientist, I think, of the 20th century, and he's still influential now. And so it's going by what he's done. Einstein was by what he's done, and you can't really. You've got an ambiguity already with its connections with the tradition of physics before Einstein.
Right.
A mistranslation of him without references, and it's probably his wife is helping him write what he wrote, and you've not got her clarification on it. So you've got him suddenly has a big, this is confusion placed into it all.
We are going to stop in 5 minutes. Okay. Yeah. Now, I know John Torday, you've got a question, but very briefly, and I don't want to discuss this now, but this has been an interesting discussion. It's been a very male discussion around a topic where one of the points that Roger's been making is the fact that women have been written out of this history. And we only have 3 women in this session. And I think this is maybe something, this is a very important issue, and I think it should be discussed in the chat. But I just want to leave that with you. It's something I've been feeling increasingly uncomfortable about during this discussion between you. But John, your question.
So I was a student of an astrophysicist for 20 years. And my recollection is that the key element, Roger, in your argument is missing is the Michelson-Morley experiment. As an empiricist, so that created pardon the pun, a vacuum, and Einstein fills the vacuum with his theory of relativity. I don't get what the argument is.
You've got the maths, and you've got Lorentz, who was trying to make sense of the Michelson-Morley experiment, and he had the same maths as Einstein was using the Lorentz transformations, but he was still talking about an ether, and that is a preferred frame. So it's a preferred frame sort of theory from Lorentz, and sort of from Einstein with it when he's saying there's no ether, when he discarded it in 1905. It's sort of like making it sound like it's discarding that part of it. And so when you're talking about special relativity, when people start saying, oh yeah, there's an ether, and other people saying there isn't, I mean, it should be Lorentz's theory, which has got the ether in it.
So you don't think it was just a paradigm?
Einstein theory hasn't.
That's why there were no references in Einstein's paper.
Sorry?
It was a paradigm shift. He didn't have to reference anyone. He went from
he was working from an earlier tradition. If you look at his group of friends, what he called the Olympia Academy, they were reading physics and so forth books. So ideally, he should have been citing references in his papers about where he was getting his ideas from, but he wasn't doing that. So he wasn't connecting it to an earlier tradition. So he still didn't, when he changed his mind in 1920 and sort of saying there is an ether, was that then meaning that he was going with Lorentz's understanding of the Lorentz transformations, or was he still saying that it was without the ether in the context of inertial frames? So you've got this understanding of the theory which has been thrown into confusion, and then it's the understanding of how to interpret what the maths means that's going thrown into confusion. It's sort of like getting back to places like CERN, where they're saying, oh, this conforms when there's accelerating particles around, or this conforms to Einstein's relativity. They're still not making it clear, those people, as to whether they're believing in an ether preferred frame when they're talking about that, or whether they're not believing in an ether preferred frame. And so they're leaving it ambiguous as to how they're interpreting these experiments.
Okay, all right. We're going to...
Okay, so I just want to say, this friend of mine set up the Einstein exhibit at the Museum of Natural History in New York.
Sorry?
Because he had access to Einstein's papers because he got his PhD at the Jerusalem University. But my impression was that Einstein had, despite his group of thought makers, he had a unique perspective, because he goes from Brownian photoelectric effect to special relativity in 1905. So he has a unique perspective. I don't think he had to reference anyone else.
Well, maybe that's the point of view of some people, but other people want to know how he gets from the existing physics to where he is at. What is he discarding? The Brownian motion, you can say, well, that's coming from Boltzmann in some way, but I don't think he's referencing that properly either. So he's not connecting all the dots for how he's doing. He's not connecting the dots.
No, stop,
so
stop, now, stop. Right. Thank you, Roger. I would say that was a very interesting talk. There are a lot of very important issues that are sitting behind what you're saying. And I think they're social issues, I think they're historical issues, and I think they're issues of the accuracy of theory. I think it's the whole package. So thank you very much, and it's been a very revealing session. John, you're tomorrow. What are you going to do?
Yeah. Well, I hope it generates as much discussion as today. Thank you, Roger, for that. I'm a bit scared now to talk about anything. I'll talk about sand, rock, music, poetry, geography, comic books, alter egos, embodied knowledge, language, the brain, nothings, sets, borders, implicate, explicate, transgressions, instructions on how to enter the other world from the belly of a giant mirrorball Trojan horse,
Brilliant.
A celebration of difference, and see more clearly, the ghost of John Hyatt will argue that there is only the ether.
Wow.
Well, I can't wait. And thank you ever so much. Thank you ever so much, Roger, for a very thought-provoking session. And see you all tomorrow. Okay. Thank you. Bye-bye.
Yeah. Thank you.
Thanks.